The limestone hills of southeastern Pennsylvania cut deep in the winter of 1754 when Johannes Meyer learned that building by the book could kill you. His first cabin followed every rule the English settlers swore by: exterior brick chimney on the gable end, thin log walls, standard and trusted construction that left his family shivering at 38 degrees inside while burning through 2 full cords of wood before February ended. Across the Pennsylvania frontier, German and English settlers alike were losing the same battle in cabins built exactly as frontier wisdom demanded, waking to frost on interior walls and empty woodsheds. Over the next 2 seasons, Johannes quietly shifted to an older method, building around a massive central stone tower that neighbors mocked as wasteful space. That single change kept his cabin 20 degrees warmer through the coldest nights, cut his wood use in half, and left his chimney warm to the touch 8 hours after the last fire died. What did Johannes understand about heat and stone that every frontier builder was missing? The Pennsylvania German settlement stretched across the limestone hills like a checkerboard of ambition and old-world memory. By 1753, families from the Rhineland and Swiss cantons had carved homesteads from the heavy timber of chestnut and oak, each cabin representing a compromise between what they knew from Europe and what the Pennsylvania frontier demanded. The immigrants carried guild knowledge in their heads and calloused hands, but the established English settlers had already set the building rules, and deviation meant isolation from supply networks, labor exchanges, and the informal codes that kept frontier communities functioning. Thomas Whitaker represented that English settler wisdom perfectly. A capable builder who had raised 17 cabins across the rolling country between Lancaster and Reading, Whitaker preached the gospel of exterior chimneys with the confidence of a man whose method had never been seriously challenged. His reasoning followed frontier logic. Place the chimney on the outside wall to maximize interior living space, use minimal stonework to reduce labor and material costs, build quickly before winter arrived, and rely on direct heat from an open hearth for cooking and warmth. Every building manual that filtered west from Philadelphia echoed this approach. Whitaker's crew could frame and stone a one-room cabin in 8 days, have the family moved in before the first hard frost, and collect their payment in grain or labor credits that kept the local economy moving. The method produced predictable results. Whitaker's cabins featured single-leaf stone walls roughly 12 inches thick, or chinked log construction with clay and moss filling the gaps. The exterior chimney consisted of fieldstone, mortared with lime and sand, rising perhaps 18 feet above the roofline with a firebox opening of 3 feet by 4 feet. Windows were minimal, usually 2 or 3 small openings fitted with oiled paper, or, for wealthier families, imported glass panes. The interior space measured roughly 16 by 20 feet, providing shelter for a family of 5 or 6 through the Pennsylvania winter. Johannes Meyer had watched 3 of his neighbors struggle through the brutal winter of 1752 using exactly this proven method. The Zimmerman family, recent arrivals from Baden, burned through 4 cords of split oak and still woke to ice on their water bucket 15 inches from the fireplace. Heinrich Stolz, a stonemason who should have known better, rebuilt his exterior chimney twice after frost cracking destroyed the mortar joints, costing him 12 days of labor and 30 pounds of lime. Most telling was the Brenner cabin, where the family abandoned the main room entirely during January. Cold snaps and crowded into the smaller back chamber, effectively living in half their built space because the exterior chimney wall became a conduit for cold rather than a source of warmth. These failures puzzled Meyer because they contradicted everything his father had taught him about masonry and heat in the old country. Johann Meyer the elder had served his apprenticeship in Strasbourg, where winter construction meant dealing with alpine conditions that made Pennsylvania seem mild. The guild tradition emphasized thermal mass, heavy stone or brick construction that absorbed heat during the day and radiated it back during the night. European farmhouses featured central masonry installations that served multiple rooms, with flue systems designed to capture and distribute heat rather than simply vent smoke. When Johannes examined his neighbors' chimneys, He saw expensive stonework performing the worst possible function, drawing interior heat outside through conduction and convection, then radiating that captured warmth into the winter air instead of back into the living space. Walking Stone, a Delaware elder who traded regularly with the German settlements, confirmed Meyer's suspicions during a February visit to examine Brenner's failing system. The Lenape had developed their own solutions for winter heating in bark-covered longhouses, using interior stone hearths surrounded by thermal mass that held warmth long after the fires died. Walking Stone traced the cold spots along Brenner's exterior chimney wall with his palm, explaining in careful English how the stone was stealing heat from the room and feeding it to the outside air. "Your people build the fire's enemy into the house," he told Meyer. "Stone should keep warmth inside, not carry it away." The social pressure against deviation ran deeper than simple building tradition. Whitaker controlled the local supply of lime mortar and maintained relationships with the quarrymen who provided cut stone. Departing from his methods meant sourcing materials independently, probably at higher cost and with delays that could push construction into winter. The German immigrants already faced suspicion about their language, their religious practices, and their agricultural methods. Challenging established building wisdom would mark Meyer as troublesome, potentially cutting him off from the labor exchanges and barn-raising cooperatives that made frontier construction possible. Meyer's own position made the risk more complicated. Unlike many of his neighbors, he possessed genuine masonry skills from his European apprenticeship, but he also needed to establish credibility in a community where English methods dominated. His first cabin had followed Whitaker's specifications exactly, partly to demonstrate that he could build according to local standards. The results, a cold, fuel-hungry structure that required constant attention to maintain basic comfort, convinced him that compromise was killing his family's chances of thriving through multiple Pennsylvania winters. The breakthrough came when Heinrich Schmidt, a joiner from the Palatinate who had worked on guild projects involving Kachelofen installations, arrived in the settlement during late 1753. Schmidt carried detailed knowledge of multi-room heating systems where several fireplaces fed into a single masonry mass, creating what he called a heat castle at the center of the house. European builders had refined these systems over centuries, learning to balance thermal mass, fuel efficiency, and interior comfort in ways that frontier practice completely ignored. Schmidt's expertise provided the technical foundation that Meyer's intuition had sensed but couldn't fully articulate. The decision crystallized during a March blizzard that killed 2 head of cattle and forced the Zimmerman family to burn furniture to stay warm. Meyer committed to building his new cabin around a central stone chimney that would weigh approximately 8 tons and occupy nearly 1/4 of his interior floor plan. Neighbors would call it wasteful. Suppliers would question the expense. But the alternative, another winter of watching good families suffer in badly designed shelters, seemed far more wasteful than extra stonework. Construction began in late April of 1754, when the frost line lifted enough to excavate the foundation. Meyer's design required a stone base extending 4 feet below ground level, far deeper than the 18-inch foundation supporting typical frontier cabins. The central chimney would carry structural loads that conventional exterior installations never faced, 8 tons of fieldstone rising 26 feet from cellar floor to roof line, with lateral forces from 4 separate firebox openings pulling in different directions. Schmidt calculated that inadequate foundation work would cause settling that could crack the flue channels or, worse, create dangerous gaps where deadly carbon monoxide could leak into living spaces. The excavation revealed the limestone bedrock that made southeastern Pennsylvania ideal for this type of construction. Meyer and his hired crew, 2 German masons and a Delaware stonecutter recommended by Walking Stone, dug a rectangular pit measuring 12 feet by 10 feet, reaching solid rock at 42 inches below grade. They laid the foundation stones without mortar against the bedrock, using the dry stacking technique that Schmidt had learned in alpine construction, where freeze-thaw cycles could destroy mortared joints. Each foundation stone weighed between 60 and 120 pounds, selected for flat-bearing surfaces that would distribute the enormous vertical load across the maximum bedrock area. Above the frost line, the construction shifted to mortared masonry, using lime sand mortar mixed with crushed oyster shell that traders brought inland from the Delaware Bay. The chimney walls rose with a thickness of 24 inches at the base, tapering to 18 inches at the roofline to reduce total weight while maintaining structural strength. Meyer positioned the chimney stack precisely at the geometric center of his planned floor area, ensuring that heat radiating from the stone surface would travel equal distances to reach the perimeter walls. This central placement created the critical 360-degree heat distribution that exterior chimneys could never achieve. The most complex challenge involved integrating 4 separate fireboxes into the single masonry mass. Meyer's kitchen firebox occupied the east face of the chimney, designed with a wide opening suitable for cooking and baking operations. The main room firebox faced south toward the anticipated seating area, with a more conventional proportions for heating and occasional cooking. 2 smaller fireboxes served the planned bedroom and storage chamber, positioned on the north and west faces respectively. Each firebox required its own primary flue rising through the masonry mass, but Schmidt's innovation lay in the secondary flue system that allowed heated air from all 4 fires to circulate within the stone walls before exiting through the main chimney opening. The interior flue design resembled a tree structure, with individual branches feeding into a common trunk. Primary flues carried smoke and combustion gases directly upward from each firebox, preventing dangerous backdrafts between rooms. Secondary channels, roughly 6 inches square, wound through the masonry mass in serpentine patterns that maximize contact between hot gases and stone surfaces. These secondary channels allowed heat that would otherwise escape through conventional chimneys to transfer into the thermal mass, where it could be stored and slowly released over periods ranging from 6 to 12 hours after the fires died. Stone selection proved critical to the system's thermal performance. Meyer rejected the easily split sandstone that most builders preferred for its workability, choosing instead dense limestone and granite fieldstone that Heinrich Schmidt tested using a simple but effective method. Schmidt heated sample stones in a bed of coals, then monitored how long they remained warm to the touch after removal from the fire. Limestone held heat for 3 hours and 40 minutes. Granite maintained warmth for nearly 5 hours. Sandstone cooled to air temperature within 90 minutes. The denser stones cost more in transportation and required more skilled cutting, but their superior thermal retention justified the additional expense. The construction technique followed European masonry traditions adapted for frontier conditions and materials. Each stone was individually fitted and shaped, with no gaps larger than half an inch between adjacent faces. The mortar served primarily to seal air leaks rather than provide structural bonding. The stones themselves carried the compressive loads through direct contact. Meyer and his crew worked in lifts of roughly 3 feet, allowing each section to cure for 5 days before adding the next level. This methodical approach consumed the entire summer of 1754, far longer than the 8-day cabin construction that Thomas Whitaker's crews routinely achieved. The structural integration with the cabin frame required careful coordination between masonry and carpentry work. Meyer built his floor joists and wall framing around the chimney mass rather than attempting to insert the chimney into a pre-existing frame. The wooden structural elements never touched the stone surfaces directly, preventing thermal bridging that could conduct heat out of the thermal mass and into the exterior envelope. Instead, Meyer used clay-packed gaps and flexible connections that allowed for differential thermal expansion between stone and wood components. Testing began immediately upon completion in late September. Meyer built small fires in each firebox and monitored the heat distribution using a technique that Walking Stone had demonstrated, placing thin birch bark strips at various locations around the chimney surface and timing how quickly they began to curl from radiant heat. The south and east faces warmed first, as expected from the prevailing wind patterns and sun exposure. More significantly, the north and west faces, traditionally the coldest areas in frontier cabins, showed substantial heat radiation within 2 hours of lighting the fires, indicating effective thermal transfer through the internal flue system. The thermal storage capacity exceeded even Schmidt's predictions. After maintaining fires in 3 of the 4 fireboxes for 6 hours, Meyer allowed all flames to die completely. then monitored the surface temperatures using the palm touch method that frontier builders relied upon before thermometers became available. The chimney surface remained noticeably warm to the touch for 11 hours and 15 minutes after the last coals died, with measurable heat radiation continuing for an additional 4 hours beyond that point. By comparison, the exterior chimney on Whitaker's demonstration cabin, built during the same period with identical fuel loads, cooled to air temperature within 3 hours of fire extinguishment. The fuel efficiency gains became apparent during the first extended test period in early October. Meyer burned seasoned oak split into 18-inch lengths, maintaining comfortable interior temperatures with approximately 60% of the wood that conventional exterior chimney systems required for equivalent heating. The multiple firebox design allowed him to concentrate fuel in whichever room required the most heat, while the thermal mass distributed that energy throughout the entire cabin structure. The first serious cold snap of November 1754 revealed a critical flaw in Meyer's otherwise revolutionary heating system. Despite the central chimney's impressive thermal storage, interior temperatures still dropped faster than Schmidt's calculations had predicted. The problem became evident during a 3-day storm, when outside temperatures plummeted to 8 degrees Fahrenheit and fierce winds drove snow through gaps around the window frames and door jambs. Even with the thermal mass radiating stored heat, Meyer recorded interior temperatures falling from 62 degrees at bedtime to 46 degrees by dawn, a 16-degree loss that consumed the chimney's stored energy too quickly and forced him to relight fires earlier than expected. Walkingstone identified the issue immediately during a post-storm visit, running his hands along the interior walls to locate the cold spots that conventional frontier construction created. The single-leaf stone walls, built according to standard Pennsylvania practice, conducted exterior cold directly through the masonry into the living space. Worse, gaps around the window and door frames created air infiltration that acted like invisible chimneys, drawing warm air out of the cabin and pulling cold air in to replace it. Good fire. Bad skin, Walkingstone observed, using a hunting metaphor that made the problem clear. The thermal mass was performing perfectly, but the building envelope was hemorrhaging the stored heat faster than the system could replace it. The solution required a complete reimagining of frontier wall construction, combining techniques that Schmidt remembered from alpine building with indigenous insulation methods that Walkingstone demonstrated using materials available in Pennsylvania forests. Meyer began the envelope improvements in early December, working during brief warm spells to avoid disrupting the family's shelter during the coldest weeks. The new wall system featured double-leaf construction with an inner stone wall separated from the outer wall by a 4-inch air gap filled with loose insulation materials. The outer wall followed conventional fieldstone construction, but Meyer reduced its thickness to 16 inches to save materials and labor while still providing weather protection and structural support. The inner wall, built with carefully selected flat stones, measured 8 inches thick and was positioned to create the insulating air cavity. This inner wall served a dual purpose. It provided thermal mass to absorb and redistribute heat from the central chimney, while the air gap prevented direct conductive heat loss to the exterior. The gap itself was filled with a mixture of dried moss, wood shavings from Schmidt's joinery work, and cattail fluff that Walkingstone gathered from wetlands near the Schuylkill River. Window modifications proved equally critical to the envelope's performance. Meyer replaced his original large openings with smaller casement windows that reduced glass area from 48 square feet to 26 square feet, cutting heat loss through the least insulated surfaces. Each window received triple protection: exterior shutters made from thick oak planks, interior storm panels fitted with oiled linen, and heavy curtains sewn from wool fabric that could be drawn tight against the window frames during the coldest nights. The shutters featured an ingenious adjustment system that Schmidt designed, allowing them to be positioned at various angles to control both heat loss and natural light admission throughout the day. The joinery work demanded precision that typical frontier construction never attempted. Meyer and Schmidt spent 4 days fitting the door frame alone, using overlapping rabbet joints and multiple weather strips to eliminate air gaps. They tested their work using a candle flame technique, holding a lit candle near potential leak points and watching for flame movement that would indicate air infiltration. Every location where the flame flickered received additional attention until the cabin achieved what Walking Stone called dead air, interior atmosphere that remained still even during exterior windstorms. Roof improvements addressed the massive heat losses that occurred through conventional frontier cabin ceilings. Meyer's original roof featured exposed rafters with no insulation above the main living space, allowing heated air to rise into the attic area and escape through the roof boards. The new design incorporated a complete ceiling system using split logs laid tight against each other, creating an air barrier between the living space and the attic. Above this ceiling, Meyer installed 12 inches of loose insulation made from sawdust, wood shavings, and dried leaves packed tight enough to prevent air circulation, but loose enough to trap dead air spaces. The steep roof pitch, increased from 30 degrees to 45 degrees, served multiple functions beyond traditional water shedding. The steeper angle created more attic volume for insulation installation, while reducing the roof surface area exposed to winter winds. Schmidt calculated that the steeper pitch also improved the stack effect in the main chimney by increasing the height differential between firebox openings and the chimney exit, creating stronger natural draft that improved combustion efficiency and reduced smoke problems. Testing the improved envelope began immediately upon completion of each section. Meyer used a systematic approach that Walking Stone had developed for evaluating winter shelter performance, monitoring interior temperatures at 6 different locations within the cabin at 4-hour intervals over multiple days. The results demonstrated dramatic improvements in heat retention. With identical fire management, lighting 3 of the 4 fireboxes for 6 hours, then allowing them to die completely, the improved envelope maintained interior temperatures above 55 degrees for 14 hours compared to the previous 8-hour period. The fuel efficiency gains compounded the thermal mass benefits in ways that Meyer had not anticipated. The better envelope meant that smaller fires could maintain comfortable temperatures, allowing the thermal mass to absorb heat more gradually and store it more effectively. During a January cold spell, with exterior temperatures averaging 12 degrees Fahrenheit, Meyer maintained interior comfort using only 3/4 of a cord per week compared to the 2 cords that his neighbor Thomas Whitaker consumed for inferior results. Air quality improvements provided an unexpected benefit of the envelope modifications. The elimination of cold drafts meant that smoke from the fireplaces no longer got pulled back into the living spaces by air infiltration, a common problem in leaky cabins that forced families to choose between warmth and breathable air. Meyer's system maintained clear interior air while delivering consistent heat distribution, allowing his family to sleep comfortably in all rooms rather than crowding around the main fireplace. The construction techniques proved scalable for frontier conditions despite their apparent complexity. Schmidt documented the methods in detailed drawings that other German immigrants could follow, noting that the materials, fieldstone, wood shavings, moss, and cattail fluff were readily available throughout southeastern Pennsylvania. The additional labor required roughly 12 days beyond conventional cabin construction, but the fuel savings over a single winter more than compensated for the extra effort. Meyer's integrated approach of thermal mass plus envelope control established a new standard for cold weather construction that began attracting attention from builders throughout the region. Frederick Miller, a contractor working on cabins near Reading, visited in February 1755 to examine the construction techniques and measure the interior temperatures himself. Miller's careful documentation showed interior temperatures ranging from 58 to 64 degrees Fahrenheit during a week when exterior temperatures never rose above 20 degrees, performance that conventional frontier cabins could not approach regardless of fuel consumption. The bitter February nights of 1755 exposed a weakness that Meyer had not anticipated in his revolutionary heating system. Despite the thermal mass performing exactly as designed and the improved envelope holding heat effectively, the cabin suffered from dangerous temperature variations between rooms. The bedroom, positioned on the northwest corner farthest from the prevailing winds, maintained comfortable temperatures near 60 degrees Fahrenheit. However, the storage chamber on the northeast side dropped to 41 degrees during the same period, creating conditions cold enough to freeze stored vegetables and making that space essentially unusable during the coldest months. Meyer's systematic temperature monitoring revealed the core problem. While the central chimney radiated heat uniformly in all directions, the air circulation patterns within the cabin created dead zones where warm air never reached. Hot air rose from the fireboxes and collected near the ceiling, but without deliberate air movement, it remained trapped in the upper portions of each room, while cold air settled at floor level. The storage chamber, which lacked its own firebox, received no direct heat input and depended entirely on air circulation from adjacent rooms, circulation that was not occurring naturally. Schmidt recognized the symptoms immediately, having encountered similar problems in multi-room Alpine houses where inadequate air distribution rendered expensive heating systems partially ineffective. The solution lay in creating deliberate air channels within the masonry mass itself, allowing heated air to flow between rooms through controlled pathways rather than depending on open doorways and natural convection. Schmidt had learned this technique from guild masters who built Kachelofen systems with integrated air distribution, but adapting the principle to Meyer's four-firebox design required significant innovation. The air distribution system that Schmidt designed featured a network of channels built directly into the chimney masonry during construction, requiring partial reconstruction of the upper portions of Meyer's chimney stack. The primary channels measured 8 inches by 12 inches in cross-section, large enough to move substantial volumes of heated air, but small enough to maintain structural integrity within the stone mass. These channels connected each firebox to distribution outlets positioned near floor level in adjacent rooms, creating a circulation loop that moved warm air to areas that lacked direct heating. The channel layout followed a hub-and-spoke pattern, with the main air plenum located at the center of the chimney mass, roughly 6 feet above the main floor level. Heated air from each firebox entered this central plenum through individual inlet channels, where it mixed and equalized in temperature before flowing through distribution channels to outlet vents in each room. The system included return air channels positioned near floor level that drew cool air back toward the central chimney, creating a continuous circulation pattern that eliminated the temperature stratification problems that plagued conventional multi-room heating. Control mechanisms allowed Meyer to regulate airflow according to seasonal needs and occupancy patterns. Each distribution channel featured a sliding damper made from shaped field stone that could be adjusted to increase or decrease airflow to specific rooms. During extreme cold periods, Meyer could concentrate heated air in the bedroom and main living areas while reducing flow to storage spaces. In milder weather, he could balance the distribution to maintain more uniform temperatures throughout the cabin. The damper design reflected Schmidt's understanding of both masonry construction and practical operation under frontier conditions. Each damper stone was individually fitted to its channel opening, with just enough clearance to slide smoothly while maintaining an effective seal when closed. The dampers were controlled by iron rods that extended through the chimney mass to adjustment handles positioned at convenient heights near each firebox. This arrangement allowed Meyer to regulate airflow without leaving the warmth of the main living areas during cold weather. Summer operation required a completely different approach to prevent the massive thermal mass from overheating the interior during warm weather. Schmidt incorporated a bypass system that isolated the air distribution channels from the main chimney flues during the summer months, preventing heated air from circulating through the living spaces when cooling was more important than heating. The bypass featured a large damper positioned in the central plenum that could be closed completely, directing all combustion air and heated gases directly up the main chimney flues without entering the distribution system. Field testing of the air circulation system began in March 1755 as soon as the masonry modifications were complete. Meyer used a smoke test technique that Walking Stone suggested, burning green wood to produce visible smoke, then observing how the smoke moved through the distribution channels and into each room. The test revealed that heated air from the kitchen firebox could reach the storage chamber within 12 minutes of lighting the fire, carrying enough thermal energy to raise the chamber temperature from 38 degrees to 52 degrees within 2 hours. The circulation system's effectiveness became dramatically apparent during the final cold snap of the 1755 winter, when exterior temperatures dropped to 4 degrees Fahrenheit for 5 consecutive nights. Meyer maintained all 4 living areas above 55 degrees Fahrenheit, using fires in only 2 of the fireboxes, the kitchen, and main room installations. The air distribution system carried heated air to the bedroom and storage chambers so effectively that those spaces required no direct fire input, reducing fuel consumption to less than half a cord for the entire cold period. Temperature measurements taken at multiple points within each room demonstrated the system's ability to eliminate dangerous cold spots. Meyer recorded temperatures at floor level, waist height, and near the ceiling in each room every 4 hours during the test period. The results showed temperature variations of less than 6 degrees Fahrenheit between the warmest and coolest locations within any single room, and variations of less than 8 degrees between different rooms. By comparison, measurements from Thomas Whitaker's conventional cabin during the same period showed temperature differences of 23 degrees between rooms and up to 15 degrees between floor and ceiling within individual rooms. The fuel efficiency improvements exceeded Meyer's expectations. The controlled air circulation meant that heated air generated by any fire was distributed throughout the entire cabin rather than being wasted in unused spaces or lost through inadequate mixing. During the March testing period, Meyer burned an average of 16 pounds of split oak per day to maintain comfortable temperatures in all 4 rooms. Whitaker's cabin, with its separate room heating approach, consumed 38 pounds of wood daily for equivalent interior comfort levels, representing a fuel saving of nearly 60%. Indoor air quality benefited substantially from the circulation system's design. The controlled air movement prevented the smoke infiltration problems that plagued cabins with inadequate airflow, while the return air channels ensured that combustion air was drawn from appropriate locations rather than creating dangerous backdrafts. Meyer's family reported no incidents of smoke-filled rooms or breathing difficulties throughout the remainder of the winter, problems that had occasionally occurred with the original 4 firebox design. The system proved adaptable to varying occupancy patterns and weather conditions. During periods when family members were away or when rooms were temporarily unused, Meyer could close the dampers to those areas and concentrate heating in occupied spaces. This flexibility allowed him to match fuel consumption precisely to actual heating needs, rather than maintaining uniform temperatures throughout the cabin regardless of usage patterns. Documentation of the air circulation techniques attracted attention from builders working on larger projects throughout southeastern Pennsylvania. Frederick Miller adapted Schmidt's damper and channel designs for a 6-room house near Lancaster, scaling up the system while maintaining the fundamental principles of central thermal mass with controlled air distribution. Miller's project demonstrated that the techniques could be applied to larger and more complex structures, establishing the foundation for what would eventually become standard practice in Pennsylvania German construction. The winter of 1800 arrived with unprecedented severity across southeastern Pennsylvania, bringing the longest sustained cold period in living memory and testing frontier construction methods beyond their normal limits. January temperatures plummeted to 6 degrees below 0 Fahrenheit and remained below 20 degrees for 18 consecutive days, accompanied by fierce northwest winds that drove snow through the smallest gaps in conventional cabin construction. The extreme conditions created a natural experiment that would definitively prove the value of Meyer's integrated heating system while exposing the catastrophic failures of standard frontier building methods. Thomas Whitaker's cabin, representing the conventional approach that most settlers still followed, suffered immediate structural damage when the extreme cold caused his exterior chimney to develop vertical cracks that extended from the foundation to the roofline. The thermal shock of repeated heating and cooling cycles, interior fires creating high temperatures against one side of the chimney wall, while the exterior face remained exposed to sub-zero air, created differential expansion that the mortar joints could not accommodate. By the 4th day of the cold snap, smoke was leaking through the cracks into Whitaker's main room, forcing his family to extinguish their primary heat source and crowd into the kitchen area around the cooking fire. The Zimmerman family faced even more serious consequences when their cabin's inadequate envelope allowed interior temperatures to drop so low that water froze in containers placed just 3 feet from their fireplace. The family abandoned their bedroom entirely and slept in the main room, using every available blanket and fur covering to prevent hypothermia. Their wood consumption reached desperate levels, nearly half a cord per day, as they struggled to maintain survivable temperatures in even one room of their home. By the 10th day of the cold period, they had exhausted their winter fuel supply and begun burning furniture and interior woodwork to keep their cooking fire alive. Meyer's cabin, by contrast, maintained structural integrity throughout the entire cold period without any signs of thermal stress or damage. The massive central chimney, protected from exterior temperature fluctuations by the thermal mass itself and the improved building envelope, experienced no cracking or mortar failure. More importantly, the integrated system of thermal mass, controlled envelope, and air distribution allowed Meyer's family to maintain comfortable living conditions in all 4 rooms using less than 1 cord of wood for the entire 18-day period, roughly 1/6 the fuel that comparable conventional cabins consumed for inferior results. The temperature measurements that Meyer recorded during the extreme weather event provided definitive proof of his system's superiority. On the coldest night, when exterior temperatures reached 6 degrees below zero with 40-mile-per-hour winds, Meyer's bedroom maintained a temperature of 58 degrees Fahrenheit at floor level and 61 degrees at waist height. The main living room remained at 63 degrees throughout the night, while even the storage chamber, the coolest area in the cabin, never dropped below 52 degrees. These measurements, taken 8 hours after the last fires had been extinguished, demonstrated the thermal mass's ability to carry the family through the longest winter nights without requiring middle-of-the-night fire maintenance. The durability advantages extended beyond simple temperature control to include long-term structural performance that conventional construction could not match. While neighbors dealt with chimney repairs, foundation settling, and envelope damage caused by extreme thermal cycling, Meyer's cabin showed no structural deterioration. The central location of the thermal mass eliminated the differential thermal stresses that destroyed exterior chimneys, while the improved envelope prevented the moisture infiltration and freeze-thaw cycles that caused conventional chinking and mortar to fail. Schmidt's careful masonry work and Meyer's attention to thermal bridging prevention created a structure that actually improved with age as the materials seasoned and settled into their final positions. The economic calculations became impossible to ignore as the cold period extended into February. Meyer's fuel consumption for the entire winter totaled 2 1/2 cords of split oak, costing him approximately $8 in labor and materials. Whitaker's conventional cabin, despite providing inferior comfort and suffering structural damage, consumed 7 cords at a cost of $22 plus an additional $6 for emergency repairs to the cracked chimney. The Zimmerman family spent nearly $30 on fuel and emergency measures, including the replacement value of furniture they had burned for heat, while still failing to maintain adequate interior temperatures. Community recognition of Meyer's achievement came gradually but decisively as word of his cabin's performance spread throughout the region. Frederick Miller began incorporating central chimney design into his building contracts, charging premium rates for what he advertised as the German warmhouse method. Other builders visited Meyer's cabin during late February to examine the construction details, measure the interior temperatures, and document the techniques for their own projects. Walking Stone brought several Delaware families to observe the heating system, leading to hybrid designs that combined indigenous insulation methods with European thermal mass principles. The knowledge transfer process revealed the scalability of Meyer's innovations across different building sizes and family circumstances. Miller successfully adapted the central chimney principle for a 6-room house near Reading, using a larger thermal mass, approximately 12 tons of stone, and a more complex air distribution system with 7 separate circulation channels. A Mennonite community near Lancaster collectively built 4 cabins using Meyer's techniques, sharing the specialized masonry labor and reducing individual construction costs while achieving uniform heating performance across all the structures. Documentation efforts ensured that the technical knowledge would survive beyond the original practitioners. Schmidt created detailed drawings showing chimney construction, damper installation, and air channel layouts, distributing copies to German immigrant communities throughout Pennsylvania and Maryland. Meyer himself began teaching the masonry techniques to younger settlers, establishing what would eventually become a recognized building tradition that persisted through the 19th century. The structural longevity of Meyer's approach became evident as conventional cabins built during the same period required major repairs or complete reconstruction within 5 to 10 years. The extreme thermal stresses of Pennsylvania winters, combined with inadequate envelope sealing and poor masonry practices, caused most exterior chimney systems to fail repeatedly. Meyer's cabin, with its protected thermal mass and integrated design, required no major structural maintenance for more than 20 years, demonstrating that the initial investment in superior construction methods paid substantial dividends over the building's useful life. Modern preservation surveys conducted by the Pennsylvania Historical and Museum Commission have identified surviving examples of central chimney construction throughout the southeastern counties, confirming that Meyer's innovations were widely adopted and adapted by subsequent generations of builders. These surviving structures, some dating to the mid-1700s, continue to demonstrate superior thermal performance compared to restored examples of conventional frontier construction, validating the technical principles that Meyer and Schmidt developed under frontier conditions. The legacy extended beyond residential construction to influence public buildings, mills, and commercial structures throughout the region. The techniques proved adaptable to larger scales and different functional requirements, establishing Pennsylvania German building practices as the preferred method for cold weather construction. The integration of thermal mass, controlled envelope, and distributed heating became standard practice that persisted until coal-fired central heating systems replaced wood-fueled heating in the late 1800s. The fundamental lesson that emerged from Meyer's work, that building performance depends on system integration rather than individual components, anticipated modern understanding of building science by more than 2 centuries. His recognition that thermal mass, envelope control, and air distribution must work together to achieve efficiency established principles that contemporary sustainable building practices have rediscovered and validated using modern materials and measurement techniques.